Okay, ladies and gents, I'll remember that you guys all left me on my own. I'm completely on my own today. Nobody's here. But don't worry, I'll be fine. I'll be fine. Okay, so what we're going to do today is pull everything we've learned together. Okay? Everything we learned about the first and the second derivative. What does it tell me about the way the curve looks like? And do kind of questions that you will find in the test. Before that, I think a little summary, a very good summary I found on page 45 in your textbook. I don't know if you got your textbook there. It might not be there yet, but you will get your textbook. It must be any minute, any day now. But anyway, I wrote it down for you. So we're looking at what happens when the first derivative is larger, smaller, or equal to 0, and combine it with information about the second derivative. We've done it all. It's just a summary. So let's look at, first of all, what happens if the first derivative is larger than 0. If the first derivative is larger than 0, that means the function goes up. But, I mean, many things can go up straight, it can go up, there's different kind of curves. So let's look at what happens when the second derivative is also increasing. Well, if the second derivative is also increasing, it's positive. If the second derivative is positive, that means the first derivative is increasing. So it's not just going up, it's going up like that, which we call it concave up. Now, if the first derivative is positive, meaning we're going up, the graph going up, but the second derivative is negative, it means that the graph is going up, but the gradient is decreasing, so it's concave down. If, however, the graph is going up, but the second derivative is 0, that really means that we are momentarily not going up or going down. Well, in fact, two things can be here, okay? Probably the most obvious thing is that we could just have a straight line going up. If it's a straight line going up, the first derivative is positive, the second derivative is 0. But there was another option we spoke about, and that's a point of inflection, okay? We actually have 2 points of inflection. I'll just pause because Rachel just came in. Okay, so we said that if the first derivative is positive, the graph is going up. If the second derivative is 0, either it's a straight line or it's a point of inflection, which could be either like that or like that as well. Am I right? Yeah. Okay, now what happens if the first derivative is negative? That means the graph is going down. But if the second derivative is positive, that means it goes down, but with an increasing gradient. What does that mean? Well, the gradient is negative, but it's just becoming less and less negative, okay? And that is going to be concave up. What happens when the second derivative is also negative? Well, that means that the gradient is not just negative, it's getting more and more negative. So that will be concave down. If the second derivative is 0, well, it's either going to be a straight line, or it's going to be some kind of point of inflection, like this, or like that. Yeah. Just check that for a second. Yeah. Ooh. Okay. Now, next thing, what happens if the first derivative is 0? First derivative is 0, really what we have is a stationary point. But what kind of stationary point will be with the second derivative, which is larger than 0? Well, it's going to be a stationary point, it's going to be a minimum. Okay? Because the gradient, which starts being negative, eventually becomes positive. Okay? That's why the second derivative is positive. And therefore, if the second derivative is negative, it's going to be a maximum. Okay? When we have a second derivative, which is 0, then again, we have a point of inflection. We can either have that or that, but we also looked at a situation where we could have we had a minimum and a maximum, and we can even have just a constant line, okay? Because it could be that they're all 0, so that's constant line. So in other words, there's a big question mark. We're not sure about it. Okay, that's about that. Let's just move on to the proper lesson now. Okay, so guys, now I'm going to do 2 questions that are very similar to what you got for what you got in the assignment. Here we're getting a function, and in fact, it's not the function, it's the derivative. It's the first derivative of function. And what they're asking me to do, again, I was supposed to draw that in the middle, but never mind. What they're asking me to do is discuss these points, A, B, C, D, E, F, G, what happens on the function. Now I will do that, but before I want to do this interesting exercise, I want to find the second derivative. Now this is something you do also in core maths. It's a very important skill to know. You get a certain function and you need to draw its derivative. Okay, because obviously the second derivative is simply the derivative of the first derivative. So we just got to ask ourselves, right, at each point, I'm just going to write a value. We are just sketching a value. So sketching a graph. I don't know obviously the numbers. But at A, what's happening at A? What happens to the first derivative? It's positive, first of all, and it's actually increasing. So if it's increasing, that means the second derivative is positive. Okay? Then at B, what happens to the first derivative? It doesn't change. It's a stationary point for the first derivative. So the second derivative will be a 0 at B. At C, the first derivative is decreasing, so the second derivative will be negative. At D, okay, we have a very low for the value for the first derivative, but it's stationary, so the second derivative now is 0. E, the first derivative is increasing, so the second derivative is positive. Okay, obviously, I don't know if it's here or there. That's why we call it a sketch. Okay? If the second derivative is 0, and G, the second derivative is also 0, okay? Because it's a stationary point. The first derivative doesn't change. And then all I've got to do is just draw the points, kind of curve them up a little bit. And now here, I'm a little bit stuck. How do I go from here to here? Well, I know, where was I? F, okay? Here the first derivative was 0, then it decreased. The first derivative decreased. That means the second derivative will slip into negative and then it go up again. So it will be like that. That is your second derivative. Now at this point I think I'm going to stop because that gives me a lot of information to talk about what's happening in A, B, C, D, and F and G. So A, okay, the graph, obviously, what do I want to say? What do I know about A? Okay, I'm going to eventually use all this information to draw F. So at A, obviously, the graph F is going up because the first derivative is increasing. But more than that, I know that the second derivative is positive. So let's have a look at that. First derivative positive, second derivative is positive. It's concave up. It's increasing upward. I don't know if it's here or there, but it's increasing upward. So this guy is going to be concave up. In B, the second derivative is 0, where the second derivative is 0, okay? But if the first derivative is still positive, so it's still going up, but it's a point of inflection. So I'm going to draw it like this. So here, it's going to go up, and it is still going to go up, but it's a point of inflection. At C, no, hang on, that was, where was I? Yes, okay. At C, the first derivative is 0, and the second derivative is negative. So now I'm going to have, maximum point. I'll try and explain why that is, okay? So A, the graph was increasing, increasing, increasing. At B, the second derivative is 0, so I've got a point of inflection. And then at C, okay, the first derivative is 0, so I've got a stationary point. The second derivative is negative, so I'm over here. So I've got a maximum point. Now let's have a look at the first derivative after C. Okay, the first derivative is negative. That means I'm going down. I'm going down, going down, going down. Until D, I'm getting a second derivative which is 0. Okay? If the second derivative is 0 and the first derivative is negative, let's find that. First derivative is negative. Second derivative is 0. I'm getting a point of inflection again. So that's going to be going down. And then before I get there, let's have a look at E. And E, okay, the first derivative is 0. So I've got some kind of stationary point. The second derivative is positive. Okay, so positive second derivative is going to be a minimum. That's not so nice. So I've got a minimum here, and I've got a point of inflection. I have a point of inflection here. Okay, where it goes from concave down to concave up. At if the first derivative is positive and the second derivative is 0, again I'm going to have some kind of point of inflection. Let's skip up to g to see what happens at g. The first derivative is 0, so I've got a stationary point. The second derivative is also, oh, that's kind of, I'm just going to pause here for a second because that doesn't make sense. Ah, yes. Right, so I've got a point of inflection here, and I've got another point of inflection there. Okay, so I've got 2 points of inflection. Both of these second derivatives are 0. Okay, so I've got point of inflection. Here, the first derivative is positive, but here, the first derivative is, no, hang on, I'm getting confused here. I think what we have here is a maximum point. I think we have a maximum point. I'll just pause this for a second and just check it to make sure, because I'm just waffling now. Okay, I almost got it. It wasn't exactly right. This is definitely an inflection point. Okay, here, if I'm looking at that, the first derivative is 0. So momentarily it's horizontal. Okay, but then it increases, becomes steeper and steeper and steeper. So what we've got here is another inflection point. It's a double inflection point. It goes from concave down, and it goes again to concave up. So we've got a double inflection point. Concave up, concave down, concave up. Okay? Hopefully that makes sense. That is a little bit difficult. Okay? The one that I gave you in the exercise, I think is a bit easier. Okay. Okay, so there was a bunch of questions here from Rachel, and let me maybe add this. It might help you. Okay? So the first derivative is obviously the derivative of the function. Now that's what they gave in the exercise. But the first derivative in itself is a function. So for example, here I can see that the first derivative is 0. Okay? So that means in the function, in E, we have a stationary point. Because we know when the first derivative is 0, then we have a stationary point. Here, the first derivative is a positive number. Okay? So we're going to have, but it's also, yeah, so the first derivative is a positive number. That means the function is growing. It's growing. Okay, I'll pause here and we'll move on to the next question. Okay, so the other question, similar question to the one I gave in an assignment, is you're getting a function and you just need to sketch it. When we sketch it, we're basically looking for the following information. We're looking for stationary points, okay, your maximum, your minimums. Then you might have points of inflections, intercepts, x and y's obviously, domain and range, so where is the function defined, and asymptotes. Okay, I'm not sure if we'll have asymptotes in this example, but maybe I'll do another one later. Okay, so we've got some kind of quadratic equation. I don't know, no, it's not quadratic, x power 4, quintic equation. Okay, so to find out the stationary point, I need to find out the first derivative. Okay, so we're going to find the first derivative, 4x cubed minus 12x squared. Okay, and now what happens in the stationary point? Well, the first derivative is 0. Okay, so we're going to have 4x cubed minus 12x squared equals 0. Okay, that happens, that's in the stationary point. Okay, we'll take 4x out, 4x, x squared minus 3. So I should have taken 4x squared. So 4x squared, x minus 3. That must be equal to 0. And I've got two options, right? I've got x equals 0 or x equals 3. Now I need to figure out, for these points, I need to figure out, are they minimum, are they maximum, or perhaps their point of inflection. So to do that, I need to find now the second derivative. So the second derivative is going to be 12x squared minus 12x, 24x. 24x. And now to figure out minimum, maximum inflection, I substitute in. Let's start with the 3. So the second derivative of 3 I'm just going to put 3 in here. It's going to be 12 times 9 minus 24 times 9. I need some help here. You're going to have the calculator on.
So 24 times 3 rather.
Let me just. Right, so obviously it was 24 times 3, not times 9, and I got 36. In other words, the second derivative of 3 is larger than 0. I wish I didn't erase that here, but maybe I'll write down here the important one. If the second derivative is larger than 0, we basically have a concave up. It's either like this or like that. Well, more than that, I'm silly here because obviously the first derivative was already 0. So in other words, it's a local minimum. Okay? So at f equals 3, I'm going to put 3 here. Okay, I will put 3 here. I might change it later. We have some kind of maximum, a minimum. I don't know if it's going to be here or be there. I'm still not sure. Okay? Well, how am I going to know? Is it here or there? I just substitute 3 in the first equation. So f of 3 is going to be, I'll need a calculator again, 3 power 4 minus 4 times 3 cubed plus 1. So I've got, what's that, 81 minus 4 times 27 plus 1.
Minus 26.
Minus 26. So it's going to be here, right? Let's say minus 26. So I've got a local minimum at 3 minus 26. Okay. Right, so that was one stationary point. I've got another suspected stationary point, let's say, at 0. Okay, we've done the 3, now let's have a look at 0. So what kind of stationary point that's going to be? We're going to substitute in the second derivative x equals 0. Well, I'm going to get 12 times 0 squared minus 24 times 0, which is 0. So second derivative is 0 as well. Now, if you remember, you wouldn't because you haven't watched it yet, when I have a first derivative 0 and second derivative 0, we don't know. It actually could be anything. I did draw it in that first thing. It could be a horizontal line, or it could be a point of inflection, or it actually could be minimum or maximum. It could be anything. And what we got to do is we actually got to check the second derivative before, a little bit before, and a little bit after. So f second derivative of f is going to be equal to 0, you see? We're going to check the second derivative a little bit before 0. Let's say minus 0, 1. I'll write it down here. And a little bit after. Okay? Let's find out, and then I'll explain what are we doing. So we just got to substitute minus 0, 1 in the second derivative. Maybe you can do that for me. So it's 12 times 0, 0, 1. Or not square. What is 0? 0, 1. Yeah. 0. You can substitute that. Write down. Let's pause that. Right, so what we're noticing here, okay, at 0, the second derivative is 0. Before 0, it's positive, and after 0, it's negative. In other words, what we see here is that there is a point of inflection. What is a point of inflection? Is a point where the concavity changes, okay? A quick reminder about that, okay? If the second derivative is larger than 0, it's concave up, which can be either like that or like that. If the second derivative is smaller than 0, it's concave down, which can be either like that or like that. So point of inflection is like the borderline between concave up, this was concave up, and here is going to be concave down. So we're going to have a graph that goes up maybe, or maybe actually goes down and then changes. Okay? So to know where it is, we need to find out what is the y value of 0. So I'm just going to put 0 inside here, okay, just to find out what is f of 0. So f of 0, that's easy, it's just 1. So I've got 0, 1 is a point. Okay, now I know it's a point of inflection, okay, so it's either going to be, shall I draw it here? You know, it's either going to be like this, something like that, or it's going to be like that. These are points of inflection. Now, at this point, I can already realize which one is, in other words, is this function got to go down or got to go up?
It's gonna go down.
It has to go down to meet that somewhere.
Yeah.
So I know I'm going to have some kind of point of inflection. Okay?
What does point of inflection?
Okay, so a little bit more about this point of inflection. Before, in negative values of x, okay, it was concave up. So it was something like this. Positive value of x, it's concave down. So it's going to be like this. And as I was just telling Rachel now here, it's not necessarily it's horizontal. Actually, it is horizontal. I'll talk about why. But the first derivative doesn't change much here. Now, how do I know it's horizontal? Because there's some point of inflection that look like this, and these one in the first video, I called it horizontal point of inflection, if you remember. How do I know it's horizontal? Because the first derivative was actually 0. Remember, for these 2 points, the first derivative was 0. If the first derivative wasn't 0, but the second derivative would be 0, that would look more like that. Okay, so we've got horizontal point of inflection. Now that's going to cross somewhere here, and then we're going to go there. And then I imagine it will cross somewhere there as well. So we found one stationary point, we found one point of inflection. Next thing is to find the intercepts. Okay, I'll just make us some, no, let's do it here. Show off with a lot of stuff to write here. So how am I going to find, how am I going to find these intercepts? I found already the y-intercept, okay, what was it? 1. Yeah, that's 1. How am I going to find that? What do I need to do?
You let
Yeah, what is equal 0 here? Y. Okay, x power 4 minus 4x cubed plus 1 equals 0. That's a little bit of a difficult equation. Let's just pause here for a second. Okay, so this example probably not the best. I mean, it's a valid example, but because if we want to find the intercept, I need to solve this equation. This is a I think it's called quintic when we have power 4. I don't have formulas for that. Okay, it's actually really, really difficult, and the only way to find it is using what we call numerical method, which we will do hopefully on Thursday. So if you remember, we'll do that one, but we will do even more difficult one. The answer is there's no what we call analytical solutions for that. There's no way to know it accurately, but computers, and we'll show you the way we do it, can find closer and closer and closer value. It might have an analytical solution, but I'm not sure. What I'm interested more doing right now is finding, there must be another point of inflection, because look, if this is concave down, and then concave up, concave down. Now this is concave up, so there must be some point of inflection. Now it doesn't necessarily need to be on the y-intercept, but it's somewhere there. And I want to just do that. They've been doing the book, but let's try and find out where is that concavity changes. Now what happens when the transition between concave up to concave down? Something is equal to 0. What is it? It's the second derivative. So I'm going to look at that equation for the second derivative, and I'm going to equate it to 0. Okay, so 12x squared minus 24x equal to 0. This is, you're going to have to do something similar for me in the assignment. Okay, so let's solve that. Let's get rid of 12, okay, so and get x out. So I'll put 12x, x minus 2 equals 0. Now there's 2 solutions. The first one should be familiar, x equals 0. We know that this was a point of inflection. But now we have another solution, x equals 2. So what we found here is the second point of inflection. Okay, it's at x equals 2. Now, just a little bit of making sure you get all your marks that you need to. All these points, the intercept, the stationary points, the point of inflection, just whatever you do, make sure that the examiner can see that you've got both the x and the y value. So here in this minimum, I wrote 3 minus 26. Here, I'm going to call this inflection point 1, 0. The intercept, we said, is beyond us. Honestly, I don't know how to solve this equation, so we can't do it. But this 2, okay, I need to still find the y. So I need to substitute 2. Let's see if I can do it in my head. 2 power 4 is 16. 16 minus 4 times 8. What is 4 times 8? 16 minus 32 plus 1. I'm getting minus 15. So that should be minus 15. This should be 2 and minus 15. That's the second point of inflection. Okay, I'll pause here and see how we do with time. Okay, there is one more example in your book which I recommend you look at it, but I don't have enough time to go over it. And to be honest, I think you can figure it out. But I would recommend looking at page 50. There's an example with cosine. And I'm not going to have that in the assignment. So I think it's for that reason it's important that you check how they solve it, just to make sure you're still happy with the trig derivatives. But let me just wrap up in 1 minute what we're doing here. So to sketch a graph, I need your stationary points and what kind of points they are, is it a maximum, minimum, points of inflection, intercept, domain, range, and asymptotes. Okay. The book tells you to start with the stationary point. I personally like to start with the intercept. I don't see anything wrong with starting with the intercept. I think it would be easier if I just drew these points. Well, in this example, I wouldn't be able to do it because I can't find these intercepts. But I don't think it's the end of the world if you start with intercept. Stationary point you find by finding the first derivative, equating it to 0. To find their nature, whether it's minimum, maximum, or points of inflection, you need to find the second derivative. Okay? Substitute the stationary points, the x of the stationary point. If it's positive, then it will be minimum. If it's negative, it will be maximum. If it's 0, you need to investigate. It could be a point of inflection. You find the intercept. Now, maybe a word about domain and range. Okay? So there are some function like, I'll write it down here, f equal 2 over 3 minus x. Now, that is not going to be defined for all x's. There will be a certain x that is not going to be defined. Which x, Rachel? Help me out here. What x f is not going to be defined? For 3. So at 3, we're talking about a different function, okay? At 3, maybe let me clear a little bit of space, okay? If I've got this, I know at 3 it's not going to be defined. And in fact, what we're going to have instead is, what do you call it?
A discontinuity.
A discontinuity, an infinite discontinuity, but we also call it an asymptote. It will be an asymptote, right? It will blow up to infinity. So it will be something like that. And if I come from if I come from the smaller than 3, it's going to blow up to infinity. If I come closer to 3, but from above 3, that's going to be negative. So it's going to be a blow up to a minus infinity. So that's what it talks about when it says asymptotes, domain.